a United Nations gen-backed system designed to coordinate global response to extinction-level threats, activates an observation campaign for an object that is not even from our solar system. Not an asteroid hurtling toward Earth, not a comet threatening collision, but an interstellar visitor that, according to every official statement, poses zero danger to our planet, an object that will never come closer than 270 million kilometers moving away from us, not toward us. So answer me this: why are astronomers worldwide being mobilized, as if preparing for something they're not telling us about? Think about that contradiction for just a second. The same network that exists solely to track potentially hazardous near-Earth objects, the same system designed for planetary defense, for impact scenarios, for threats that could actually reach us, and they're deploying it for something already leaving the solar system. This isn't an adaptation. This isn't expanding their mandate. This has never happened before in the 11 years since the International Asteroid Warning Network became operational. Not for Umomosha in 2017, the first confirmed interstellar visitor, not for Borisov in 2019, the first interstellar comet, but for 3I Atlas, the third interstellar object we've detected. Suddenly the rules change. The timing alone should make you pause. 3I Atlas spent weeks hidden behind the sun, invisible from Earth during what astronomers call solar conjunction. The moment that alignment ends, the moment we get our first clear view, the campaign launches, same day, October 21. As if they were waiting. As if the timing wasn't coincidence but coordination. And just 8 days later, October 29, the object reaches perihelion, its closest point to the sun. Whatever they needed to observe, whatever triggered this unprecedented activation, it required seeing 3I Atlas at that exact moment in its trajectory. Here is what doesn't add up. Yawn campaigns are designed for objects that might impact Earth. That is their mandate. That is the entire reason the network exists. NASA's own calculations confirm 3I Atlas will never threaten us. It is leaving. So, why activate planetary defense protocols for something that isn't defending us from anything? Unless the threat isn't about physical impact, unless what they're monitoring isn't collision risk, but something else entirely. Something they've chosen to frame as a training exercise while mobilizing resources that suggest anything but routine practice. The official explanation sounds reasonable on the surface. They're using 3I Atlas to refine observation techniques, to practice coordination, to improve the astrometry methods that would be critical if a genuine threat appeared. And yes, that makes strategic sense. Planetary defense requires rehearsal. But drill scenarios don't usually involve registration deadlines and mandatory workshops with restricted access. They don't usually coincide with unverified but persistent reports of aerospace gen-grade nickel compounds in the object's emissions. Compounds that, according to Dr. A.V. Loeb of Harvard, have specific characteristics seen primarily in industrial manufacturing in factories in technology. Now, before you write this off as conspiracy thinking, understand what we're dealing with here. This isn't speculation about secret bases or hidden agendas. This is documented mobilization of international scientific resources on an unprecedented scale, targeting an object with chemical signatures that don't match any natural comet in our databases, during a 2-10-month observation window that represents humanity's only chance to study this visitor before it vanishes into interstellar space forever. Those are facts. The question is what those facts mean. If this story has you leaning forward, if you've been following 3I Atlas and something about the official narrative feels incomplete, then you're already part of something larger, a global network of people who pay attention while headlines simplify and mainstream coverage moves on. Hit that like button right now so this reaches others who need to see it. Because what happens between now and January 7th, 2020-6, when this campaign officially concludes, might rewrite our understanding of what is possible. Drop a comment telling me where you're watching from. This isn't an American story or a European story. This is a coordinated international response, and I want to see how far across the planet this community reaches. And subscribe because I'll be covering every development as it unfolds. The November workshop that only registered participants can attend. The observation data as it emerges throughout December. The findings when the campaign ends in late January. This is happening in real time, which means we're not looking back at history, we're watching it form. You're not passive observers by questioning. By refusing surface explanations without critical examination, you're ensuring transparency remains possible to understand why a harmless interstellar comet has triggered the first ion campaign of its kind. We need to start with what happened the moment solar conjunction ended, and the world finally got a clear look at what is actually out there. October 20, 2020, 5. The Minor Planet Center at Harvard University. the official global clearinghouse for every asteroid and comet observation made by humanity, publishes an IORN bulletin that rewrites the playbook. Campaign target, 3I Atlas. Campaign dates, November the 20 Gen 7th, 2020 Gen 5 through January 20 Gen 7th, 2020 Gen 6. Exactly 2 months. Campaign objective, exercise the capability of the observing community to extract accurate astrometry from a distant interstellar comet. That phrasing matters. Not scientific opportunity. Not observation of interest. The word is exercise. Military language, preparedness language, the terminology you use when testing readiness for scenarios you might actually face. Let's establish context. The International Asteroid Warning Network has been operational since 2014, established following United Nations recommendations for coordinated planetary defense. In over a decade of monitoring near-Earth objects, tracking potentially hazardous asteroids, coordinating observations of comets passing through the inner solar system, they have never, not once, launched a formal campaign for an interstellar visitor. Oumuamua received intensive study from individual observatories, yes, but no IORN mobilization. Borisov was observed extensively by professional astronomers worldwide, certainly, but no campaign structure, no registration requirements, no mandatory workshops. 3I Atlas is different. The question that should bother you is why. Solar conjunction is when Earth, the Sun, and a celestial object align with the Sun in the middle, making observation impossible. The Sun's glare drowns out everything behind it. For weeks, 3I Atlas was invisible, hidden in that optical dead zone. Astronomers knew it was there. They could calculate where it should be, but they couldn't see it, couldn't observe its behavior, couldn't analyze its composition, couldn't track changes in brightness or trajectory. They were essentially flying blind. The moment that conjunction ends, the moment the object emerges from behind the Sun into observable space, the announcement drops. Same day. That is not reactive, that is planned. They were ready. Consider what that coordination implies. The bulletin didn't go through weeks of bureaucratic approval. It didn't require committee meetings and consensus-building delays. It was ready to publish the instant observation became possible again, which means the decision to launch this campaign was made earlier, during conjunction, when they couldn't even see 3I Atlas based on what data from before conjunction. Preliminary observations that showed something significant enough to justify this response, or projections about what they expected to find once the object became visible again. The timeline compresses immediately. Registration deadline, November 7th. That gives observers exactly 17 days from announcement to commit. For astronomical campaigns, that is absurdly tight. Professional observatories schedule telescope time months in advance. Research grants require planning. International coordination demands logistics. Yet, they're demanding commitment within 2.5 weeks. The message is clear: drop whatever else you're doing. This takes priority. This matters now. And it is not open participation. There is a mandatory workshop on November 10th. Attendance required for campaign eligibility. Think about what that means. Astronomy is traditionally collaborative and open. Observations are published. Methodologies are shared. Data is made available to the global scientific community, but this campaign requires controlled access. You must register by November 7th, attend the workshop on November 10th, and only then do you receive clearance to participate in observation, starting November 20 Gen 7th. What are they teaching in that workshop that requires restricted access? What astrometry techniques need closed training sessions before deployment? The official explanation emphasizes improving comet astrometry methods. That is entirely plausible. Comets are genuinely difficult to measure accurately because their gas emissions create brightness halos that distort position measurements. Get the center point wrong by even a fraction, and your trajectory calculations become increasingly inaccurate over time. For planetary defense, the inaccuracy could mean the difference between detecting an impact threat and missing it entirely. So using 3I Atlas as a test case makes strategic sense. It is a comet. It is observable. It is harmless. Perfect training scenario, except there are comets passing through the inner solar system constantly, dozens observable at any given time. Comets with well-studied compositions, predictable behaviors, and orbital characteristics we've tracked for years. Yet IORN chose 3I Atlas. The interstellar visitor, the object moving at 210,000 kilometers per hour on a hyperbolic escape trajectory. The one with chemical signatures that don't match established comet profiles. The one that, according to multiple observatories, exhibits an anti-Zen tail phenomenon never before documented in solar system comets. That is the training target they selected, not a typical comet. This one, Yorn's history provides contrast. Since 2014, they've coordinated on hundreds of near-Zen Earth objects, asteroids that pass within lunar distance, comets on approaches that warrant monitoring, objects with even marginal impact probabilities. Standard procedure involves tracking, data sharing, and threat assessment. But formal campaigns with registration requirements and mandatory workshops, those are reserved for high-Zen priority scenarios, objects that demand concentrated, coordinated response. The kind of response you mobilize when stakes justify the cost, and the cost is substantial. Telescope time on premier instruments like the James Webb Space Telescope or the Hubble Space Telescope runs tens of thousands of dollars per hour. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, the European Space Agency's Mars Express, all have committed resources to 3I Atlas observation, not opportunistic observation when time permits. Dedicated time, scheduled observation windows. That represents millions of dollars in equipment costs, personnel hours and operational expenses for training. For practice, that is extraordinarily expensive practice. The bulletin language is precise. Exercise the capability of the observing community to extract accurate astrometry. Break that down. Not develop capability, not build capability, exercise capability, as in test capability that already exists to ensure it functions under real Zen world conditions. They're not teaching observers something new, they're confirming that existing techniques work when applied to challenging targets. That is what you do before you need those techniques operationally. You validate them, you stress test them, you confirm your systems perform under pressure. But here is where the explanation strains. If this is purely procedural validation, why the urgency? Why the restricted access? Why this specific object with its unprecedented characteristics? Training exercises work best with representative scenarios, not anomalous ones. You don't teach someone to drive by putting them in a vehicle that handles unlike anything they'll encounter on actual roads. You use standard examples. Yet they've chosen the most unusual interstellar visitor we've detected, unusual in composition, behavior, and observational characteristics, as the test case for planetary defense coordination. The registration requirement deserves attention. IORN invited not just professional observatories but citizen scientists, amateur astronomers with backyard telescopes. That is unprecedented for an IORN operation. Professional coordination is standard. Citizen inclusion is not. It suggests they need volume, maximum coverage, as many observation points as possible distributed globally, capturing data from diverse locations and conditions. That is consistent with validation testing. You want redundancy. You want multiple independent measurements to confirm accuracy, but it is also consistent with something else. With verification, with needing enough observers that consensus becomes undeniable. November 20 Zen 7th to January 20 Zen 7th. 2 months. That window captures 3I Atlas's optimal post-Zen perihelion observation phase. After perihelion on October 20 Zen 9th, the object begins moving away from the Sun, gradually dimming as distance increases. By late November, it is still bright enough for detailed study. By late January, it approaches the threshold of detectability for all but the largest telescopes. The campaign window represents our last clear look after January. 3I Atlas fades into the cosmic background forever. Everything we learn in these 2 months. Everything we miss permanently. That finality adds weight. This isn't like tracking an asteroid we can observe for years. This isn't a comet on a predictable orbit we'll see again in decades. This is one pass, one opportunity. And they've structured an international campaign around maximizing that opportunity, while framing it as routine training. Both can be true, but only one fully explains the scale of mobilization. So, we're left with a documented activation that breaks precedent, targets an anomalous object, demands rapid commitment, restricts participation through mandatory training, coordinates global resources on an unprecedented scale, and operates under a compressed timeline that represents our only chance to study this visitor. The official explanation accounts for much of that, but not all of it. And the gaps between what makes sense and what is actually happening, those gaps are where questions live. To understand what makes those questions necessary, we need to understand the technical challenge they claim to be addressing. Because if improving comet astrometry is truly the objective, then the difficulty of that task, the stakes of getting it right, and the unique challenges 3I Atlas presents need to be clear. Only then can we evaluate whether the response is proportionate to the stated goal or whether something else is driving this mobilization. Astrometry. The word sounds technical, abstract, like something only specialists need to understand. But the concept is remarkably simple, and the stakes are existential. Astrometry is how we track objects in space, how we measure their positions against the fixed background of stars, how we calculate their velocities and trajectories, how we predict, sometimes years in advance, exactly where an asteroid or comet will be at any given moment. Get it right, and we can plan deflection missions, coordinate observations, and protect Earth from impact threats. Get it wrong, and a potentially hazardous object might arrive unannounced. The method itself is ancient. Navigators used it for centuries. You photograph an object against background stars whose positions we know with extreme precision. Those stars are reference points. By measuring how the object moves relative to those fixed points over time, you calculate velocity and direction. Modern astrometry uses digital sensors instead of human eyes, computer processing instead of manual calculation. But the principle remains unchanged. It works beautifully for asteroids, solid objects, discrete points of light. You measure the center, track the motion, calculate the orbit. Clean, precise, reliable. Comets destroy that simplicity. Comets aren't discrete points, they're surrounded by comas. Vast clouds of gas and dust vaporizing off the nucleus as solar radiation heats the icy surface. That coma can extend hundreds of thousands of kilometers. It glows, it scatters light. It creates a diffused brightness distribution that obscures the actual nucleus hidden at the center. And here is the problem. Telescopes see the brightness, not the nucleus. They measure the center of that glowing cloud, not the center of the solid object producing it. And those two centers don't necessarily align. Imagine trying to locate the exact center of a streetlight on a foggy night. The bulb itself is small, maybe a few centimeters across, but the glow diffusing through the fog extends meters in every direction. Where do you measure? The brightest point in the haze, the geometric center of the glow. Your best estimate of where the actual bulb must be behind all that scattered light. Small errors in that estimate multiply rapidly. One night's measurement might be off by a meter. Measure again the next night from a different angle. The fog has shifted. Your error is different. Try to calculate the streetlight's movement based on those inconsistent measurements, and your predictions become increasingly wrong. That is the comet astrometry problem at cosmic scale. The nucleus of 3I Atlas is somewhere between 440 meters and 5.6 kilometers in diameter. The coma extends hundreds of thousands of kilometers. Measuring the nucleus position to within a kilometer sounds precise until you realize that a 1 kilometer error tracked over weeks translates to thousands of kilometers of position uncertainty. And if you're trying to predict whether a comet will impact Earth months or years in the future, those errors compound into complete trajectory unpredictability. The IORN Bulletin states this explicitly. Cometary bodies are extended with morphological features that can systematically pull their centroid measurements off their central brightness peak, presenting challenges to estimate comet trajectories. Translation. Comets have shapes and structures that distort brightness measurements, making position calculations systematically inaccurate. Not randomly inaccurate, systematically. Meaning the errors are consistent and predictable once you understand them, but devastating if you don't. And the consequences aren't academic. If a comet were discovered on an Earth impact trajectory and our astrometry techniques couldn't accurately track its position, we might calculate the wrong impact point, launch a deflection mission to the wrong location, or worse, miss the threat entirely until impact was imminent. Consider the success story. In 2008, astronomers detected a small asteroid designated Launtzer-Nimbar TC-10, approximately 19 hours before it entered Earth's atmosphere, over Sudan. They tracked it precisely enough to predict the impact location within kilometers. Search teams recovered fragments of the meteorite based on those predictions. That is astrometry working perfectly. The object was an asteroid, solid, well-defined, and we had it tracked so accurately that we knew 19 hours in advance exactly where it would land. That is the capability planetary defense requires. Now, imagine the same scenario with a comet. The nucleus is hidden in a coma. Brightness fluctuates as gas jets activate and deactivate on the surface. The coma itself acts like a sail, creating non-Zen gravitational acceleration as solar radiation pressure pushes against the gas cloud. Your trajectory calculations keep shifting because the object's path keeps changing in ways gravity alone can't explain. That is why comet astrometry is hard. and why the IORN bulletin frames 3I Atlas as an opportunity to improve those techniques before facing a real threat. That explanation is responsible. It is forwards and thinking. Using a harmless interstellar comet as a test case before confronting an actual dangerous comet is smart strategy. But here is where the narrative starts straining under scrutiny. Comets pass through the inner solar system regularly. We detect dozens each year. Some are new visitors from the Oort cloud. Some are periodic comets returning on predictable schedules. All of them present the same astrometry challenges. Any of them could serve as training targets. Yet IORN selected 3I Atlas, the first interstellar comet to receive this treatment. Why? The answer might lie in what makes 3I Atlas uniquely challenging. Its velocity is extraordinary. At 210,000 kilometers per hour relative to the solar system, it is moving nearly twice as fast as Earth orbits the Sun. That speed means observation windows are compressed. Measurements must be made quickly and accurately because the object's position changes rapidly. There is no time for leisurely observation campaigns stretching over years. This is accelerated planetary defense simulation. The kind of compressed timeline you'd face if an impactor were detected with minimal warning. Its orbit is hyperbolic, not elliptical like solar system comets that return periodically. Hyperbolic means it is not bound by the Sun's gravity. It is passing through once, never to return. That creates urgency. Miss your chance to observe, and there is no second opportunity. No future apparition to correct mistakes or gather additional data. Everything learned happens now or never. From a training perspective, that simulates the pressure planetary defense teams would face under real threat conditions, and its composition is unknown. Every solar system comet we've studied formed from the same primordial material that created our Sun and planets 4.6 billion years ago. We have models, we have decades of spectroscopic data, we know what to expect. 3I Atlas formed elsewhere around a different star in a stellar environment with potentially different chemistry. Our models might not apply. Our expectations might be wrong. That forces observers to work without assumptions, to validate measurements against uncertain baselines, to develop techniques that don't rely on prior knowledge of the target. That is valuable training for unexpected scenarios. So yes, 3I Atlas makes a challenging training target. The speed, the hyperbolic trajectory, the unknown composition, all of that creates realistic pressure that tests observation networks under difficult conditions without actual danger. That justifies some level of coordinated response. But does it justify the scale we're seeing? Does it justify mandatory workshops, restricted participation, and mobilization of the world's most advanced observational assets? Or does the challenge of 3I Atlas explain only part of why this campaign exists, while something else, something about the object's observed characteristics beyond just being challenging to measure, explains the rest? The chemical anomalies, the spectroscopic data emerging from observatories worldwide, doesn't simply show a difficult Zen-to-Zen measure comet. It shows chemical signatures that don't match any comet we've studied before. Not just unusual, according to some researchers, impossible under natural formation scenarios. And those signatures were detected before the campaign was announced, which means the decision to mobilize IORN wasn't based solely on 3I Atlas being a good training target. It was based on something they saw, something in the data, something that made this object specifically worth the unprecedented response. To understand what that might be, we need to look at the object itself, not the orbital mechanics, not the observation challenges, the actual physical characteristics, the size estimates, the velocity, the chemical composition, and the specific anomalies that have researchers using words like unprecedented and inconsistent with known natural processes. Because once you see what makes 3I Atlas strange, the question stops being, why use this for training, and becomes, are they training, or are they investigating? Let's start with size, because scale matters. 3I Atlas is estimated between 440 meters and 5.6 kilometers in diameter. That is an enormous range, which itself tells you something about observation difficulty. But take the extremes. At the small end, 440 meters, you're looking at an object roughly the size of the Chrysler Building in Manhattan standing on end. At the large end, 5.6 kilometers, you're looking at the entire length of Manhattan Island from Battery Park to the Harlem River. Neither estimate puts 3I Atlas in planets in killer territory. An object this size wouldn't cause global extinction if it impacted Earth, but it would be catastrophic on a continental scale. Cities destroyed, regional climate disruption, millions of casualties. It is not civilization Zen ending, it is civilization Zen altering. It is not headed toward us. NASA's calculations confirm that explicitly. Closest approach was 1.8 astronomical units. roughly 270 million kilometers. For perspective, Mars at closest approach comes within about 50-5 million kilometers of Earth. 3. Atlas never came anywhere near that close. It passed through the inner solar system, swung around the Sun at perihelion on October 2019, and is now leaving on a hyperbolic trajectory that will carry it back into interstellar space. We're safe physically, but the size tells us this isn't some icy pebble. This is a substantial object with significant mass, and whatever processes shaped it over billions of years created something large enough to be geologically complex. The velocity demands attention. 210,000 kilometers per hour. That translates to roughly 50-8 kilometers per second. Earth orbits the Sun at about 30 kilometers per second. 3I Atlas is moving nearly twice that fast, which makes perfect sense for an interstellar visitor not bound to our solar system. But consider what that speed means for observation. Every second, the object travels 50-8 kilometers. Every hour, 210,000 kilometers. By the time you photograph it, process the data, and prepare for the next observation, it is already thousands of kilometers from where you measured. Astrometry under those conditions requires precision timing and rapid data processing. There is no room for delay. Now the chemistry, and this is where things stop being merely interesting and start being genuinely strange. In September 2020 Gen 5, the James Webb Space Telescope analyzed 3I Atlas using infrared spectroscopy, essentially measuring which wavelengths of light the comet absorbs and emits to determine composition. The data showed elevated carbon dioxide in the coma, significantly more carbon dioxide than water vapor. Most comets in our solar system are water than ice dominant. Dirty snowballs. Essentially, when solar radiation heats them, water sublimates off the surface, creating the characteristic coma and tail. 3I Atlas is chemically different. All rich, that is not impossible. There are solar system comets with elevated carbon dioxide, but it is unusual enough to stand out. Unusual enough that astronomers started asking, where did this object form? The hypothesis emerged quickly. Perhaps 3I Atlas formed in the outer regions of its home stellar system, far from its parent star, where temperatures were cold enough that carbon dioxide remained frozen while water vapor had already escaped. That would explain the composition difference. It is a natural process. It fits known physics. It just requires formation conditions slightly different from those that created solar system comets. Perfectly plausible. But then the nickel showed up. October 2020 Gen 5, the Keck Observatory in Hawaii and the Very Large Telescope in Chile, both equipped with advanced spectrometers, detected something unexpected. Neutral nickel vapor in 3I Atlas's coma. Specific wavelengths 350 Zen 2 nanometers, 340 Zen 1 nanometers. These are atomic emission lines. The spectroscopic fingerprints that identify specific elements. The detection was clear. Multiple observatories confirmed it independently. Nickel vaporizing off the surface or nucleus, carried outward in the gas emissions, glowing at those characteristic wavelengths. And immediately researchers started trying to explain how that could happen naturally. Nickel exists in comets. That is not the mystery. Most cosmic objects contain metals. They're formed in stellar cores ejected during supernovae, incorporated into the dust and gas that eventually condenses into new stars and their planetary systems. Finding nickel in a comet isn't shocking. What is shocking is finding nickel vapor at the temperatures and conditions where 3I Atlas exists. Nickel has a high vaporization temperature. You need sustained heat well over 1000 degrees Celsius to produce the kind of vapor emissions observed in the spectroscopic data. 3I Atlas, even at perihelion, is far too cold for that kind of natural vaporization. Solar radiation can heat comet surfaces. Yes, but we're talking about localized heating on the sunward side, not sustained high temperatures throughout the entire object. For nickel to appear in the coma at observed intensities, either there is a mechanism concentrating heat far beyond what solar radiation alone can produce, or the nickel is being released through some process other than simple thermal vaporization. Neither explanation fits standard comet behavior models. This is where researchers started using the word anomalous. And then there is what is missing: iron. Nickel and iron are cosmic siblings. They form together in stellar nucleosynthesis. They're expelled together in supernovae. They bond together in asteroids and meteorites. The nickel-Zen-iron ratio in cosmic objects is remarkably consistent across our solar system. Finding nickel without corresponding iron is like finding smoke without a heat source. Technically possible, but it demands explanation. It violates the expected pattern so completely that its absence becomes more significant than the presence of nickel itself. Dr. A.V. Loeb, chair of Harvard's astronomy department and one of the researchers analyzing 3I Atlas data, noted this discrepancy immediately. The nickel ratio doesn't match any known natural comet or asteroid composition in our databases. It is not slightly off, it is dramatically inconsistent. And Loeb went further, pointing out that certain nickel compounds, specifically nickel tetracarbonyl, exhibit characteristics similar to what is being observed. Those compounds are stable at much lower temperatures than pure nickel. They could explain the vapor emissions without requiring impossibly high heat. There is just one problem. Nickel tetracarbonyl is primarily known from industrial processes, from chemical manufacturing, from technology. Now, before this becomes conspiracy speculation, let's be clear about what Loeb is actually saying. He is not claiming 3I Atlas is artificial. He is noting that the observed nickel signatures are more consistent with certain manufactured nickel compounds than with natural nickel deposits. He is suggesting that possibility warrants investigation, not because it is likely, but because ruling it out requires gathering more data rather than assuming natural explanations that don't fit observations. That is scientifically responsible. Extraordinary claims require extraordinary evidence, but so does dismissing anomalous data without thorough investigation. Other astronomers have proposed natural explanations. Perhaps 3I Atlas formed in an unusually metal-rich stellar nebula, where nickel condensed preferentially over iron due to specific temperature and pressure conditions. Perhaps its composition reflects stellar processes we simply don't fully understand yet. Perhaps there is a chemical mechanism that concentrates nickel while depleting iron that we haven't identified, because we've never studied an interstellar comet with this level of instrumental sensitivity. All of those are plausible. None have been confirmed, and that uncertainty is what makes 3I Atlas scientifically compelling. Then Hubble observed the anti-gen tail. Comets develop tails as solar radiation, and solar wind push gas and dust away from the nucleus. The tail always points away from the sun. That is basic physics. Radiation pressure, solar wind. The forces that shape comet tails are well understood and completely unidirectional. But Hubble images from September 2020 Gen 5 showed 3I Atlas with a secondary feature pointing toward the sun, an anti-gen tail. Not exactly opposite the main tail, more like a forwards-and directed jet or stream. Loeb and his colleagues offered a potential explanation. Ice fragments reflecting sunlight differently than dust could create an optical illusion of particles moving sunward, when they're actually moving outward at different velocities. Larger particles travel slower, smaller particles travel faster, creating separation that looks like motion in the opposite direction when viewed from specific angles. It is a perspective effect, not actual reverse motion. That explanation fits physics. It has been proposed for similar features observed in solar system comets, though never confirmed with the clarity that Hubble images of 3I Atlas provide. But here is what makes the anti-gen tail significant. This feature had never been documented with this degree of certainty in any solar system comet before. Proposed, yes. Theorized, yes. Observed with this specificity, no. 3I Atlas represents the first clear case where we can study this phenomenon in detail from a scientific perspective that is valuable. It helps confirm theoretical models, but from a pattern recognition perspective, it is another unprecedented characteristic stacking on top of unusual composition and anomalous nickel emissions. None of these characteristics individually prove anything extraordinary. All rich composition, unusual but natural. Nickel vapor, anomalous but potentially explainable. Missing iron, strange but not impossible. Anti-gen tail, rare but theoretically consistent with known physics. The question isn't whether any single anomaly is impossible. The question is whether the combination of multiple anomalies in the same object, an object already unprecedented by virtue of being interstellar, rises to the level that justifies the response we're seeing, and we haven't even addressed the age estimates. Analysis of 3I Atlas's trajectory and velocity suggests it has been traveling through interstellar space for at least 7 billion years. Our solar system is 4.6 billion years old. 3I Atlas is older than the Earth, older than the Sun. It formed around a star that might not even exist anymore. Whatever processes shaped its composition occurred under conditions we can only infer from models and simulations. We're looking at a time capsule from a stellar environment billions of years removed from anything we can directly observe. So, here is what we know for certain. 3I Atlas is large, fast, chemically unusual, exhibiting emission patterns that don't match known comet behavior, missing expected elements, displaying rare optical phenomena, and older than our planetary system. That is documented. That is verifiable through multiple independent observations. The question isn't, are these characteristics real? They are. The question is, do these characteristics explain why or inactivated? And maybe they do. Maybe unprecedented science justifies unprecedented response. Or maybe the anomalies suggest something worth monitoring with every asset we have. The official explanation for the IOD campaign frames this as training, as preparation for future threats using a convenient test case. And as we've acknowledged, that explanation makes strategic sense. But there is another explanation, one that is more mundane than artificial intelligence, but more significant than routine science. And that explanation requires understanding what planetary defense drills actually look like, and whether what we're seeing matches the profile or suggests something else. Let's give the official explanation the serious consideration it deserves. Because dismissing it as a cover story without examining its merits would be intellectually dishonest. NASA's Planetary Defense Coordination Office and the International Asteroid Warning Network exist for one purpose: to protect Earth from asteroid and comet impacts. That mission requires capabilities we've only recently begun to develop: detection networks, tracking infrastructure, international coordination protocols, deflection technologies, and critically, all of those capabilities require practice. Not simulations, not computer models, real observations of real objects under real conditions. Consider what we accomplished in September 2020 Gen 2. NASA's DART mission, Double Asteroid Redirection Test, deliberately crashed a spacecraft into Dimorphos, a small asteroid moon orbiting the larger asteroid Didymos. The impact successfully altered Dimorphos's orbital period, proving that kinetic deflection works. We can move asteroids, we can change their trajectories. The physics is solid, the technology is operational. That is a historic achievement. Humanity now possesses demonstrated capability to defend against cosmic impacts. But DART had advantages that real Zen-world scenarios might not provide. Dimorphos was a known quantity. Astronomers had tracked it for years. They knew its orbit precisely. They knew its size, its rotation, its relationship to Didymos. DART launched 10 months before impact, giving engineers time to refine the trajectory, make course corrections, validate systems. The impact point was calculated with extreme precision. When DART hit, it hit exactly where planned. But here is what DART didn't test: finding an unknown object with minimal warning and tracking it accurately enough to plan an interception mission under time pressure. Deflection is useless if you can't track the target. Think about the operational sequence. Telescope detects object. Initial observations establish basic trajectory. Astrometry refines position measurements. Orbit calculation determines if impact is likely. Threat assessment evaluates potential damage. If threat is confirmed, deflection planning begins. But every step in that sequence depends on accurate position data. A tiny measurement error at the detection phase compounds into massive trajectory uncertainty weeks later. If you can't predict where the asteroid will be, you can't plan an intercept, you can't time the deflection correctly, the mission fails. And if the object is a comet, difficulty multiplies. Asteroids are predictable. Comets outgas. They develop non-Zen gravitational acceleration as vapor jets act like tiny thrusters, subtly changing trajectory in ways gravity alone can't explain. That makes comets harder to track and harder to deflect. Outgassing is unpredictable. You can't model what you can't predict, and you can't intercept a target whose path keeps changing in ways your calculations don't account for. From this perspective, 3I Atlas truly is an ideal training target. It is a comet, so observers must deal with all the astrometry challenges that come with measuring diffuse objects. It is moving fast, creating time pressure similar to what responders would face during an actual short-Zen warning threat. It is interstellar, meaning its composition is unknown and can't be predicted from existing models. And crucially, it is harmless. Zero risk. Mistakes cost nothing except learning opportunities. That is perfect for stress Jan testing systems. The campaign structure mirrors real planetary defense response. Registration establishes who is participating. The workshop trains participants on standardized methodologies, so everyone's measurements are compatible. The observation window creates sustained coordinated effort. Data aggregation tests whether real Zen time information sharing works across international borders. This isn't abstract planning. This is operational validation. Testing whether the infrastructure works when activated under realistic conditions. And let's acknowledge the wisdom in running this drill now, while there is no active threat. Planetary defense infrastructure is relatively new. DART flew just 3 years ago. IORN has existed for only a decade. The protocols are untested at scale. What happens when multiple countries need to share telescope time? Who prioritizes conflicting observation schedules? How quickly can data be validated and integrated? These aren't hypothetical questions. They're operational challenges that determine whether planetary defense succeeds or fails. Better to discover problems during a drill than during a real crisis. There is also precedent for using real objects as training scenarios. Military pilots train against actual aircraft, not just simulators. Firefighters practice on controlled burns, not just classroom exercises. Surgeons refine techniques on complex cases before facing emergencies. The principle is universal. Training under realistic conditions produces better readiness than artificial simulations. 3. IATLAS provides realistic conditions without actual danger. That is valuable enough to justify significant resource investment. The international cooperation aspect deserves emphasis. Planetary defense isn't a national concern. It is a species GAN-level concern. An asteroid doesn't recognize borders. Impact anywhere affects everyone. So response must be coordinated globally. That requires infrastructure, agreements, protocols, and most critically, trust. Countries must share data, pool resources, and coordinate actions despite political differences. The 3I Atlas campaign tests whether that cooperation functions effectively. Can observatories worldwide collaborate on tight timelines? Can data sharing happen in real time? Can consensus be reached quickly enough to matter? Those are questions worth answering before facing actual threats. So yes, the drill hypothesis makes sense. It is responsible. It is forward Zen thinking. It justifies much of what we're seeing. The tight timelines, the coordinated structure, the international participation, the resource investment. All of that aligns with validating planetary defense readiness using a convenient real Zen world target. That is the charitable interpretation, the reasonable interpretation, and it might be completely accurate. But here is where doubt creeps in. Drills are designed around representative scenarios, not exceptional ones. You train people on typical challenges they'll likely face, not edge cases that might never occur. Yet 3I Atlas isn't typical. It is the most chemically anomalous interstellar object detected. It exhibits characteristics no solar system comet has shown. It is faster, older, and compositionally stranger than the comet's planetary defense would likely face from within our system. So why choose this specific object for training when dozens of more representative comets are available? The timing bothers me. The announcement came the day solar conjunction ended. That means the decision to launch this campaign was made during conjunction. When direct observation was impossible, what prompted that decision? What analysis conducted before they could even see 3I Atlas clearly again justified mobilizing international resources on this scale? Preliminary data from before conjunction showed the chemical anomalies, the nickel detection, the unusual composition. So they knew 3I Atlas was strange before deciding to make it the focus of an unprecedented IORN campaign. The anomalies weren't discovered during the campaign, they preceded it, which means the campaign might be a response to those anomalies as much as a training opportunity. And there is the restricted access, the mandatory workshop, the registration requirements. Those don't match typical open scientific collaboration. When astronomers discover something interesting, the usual response is broad invitation. Hey everyone, look at this. We need more data. Instead, IORN created barriers, prerequisites, controlled participation. That suggests they want specific people with specific training contributing data, which makes sense for standardization. But it also means they're filtering who gets access to the campaign's real Zen time data integration. Only participants see the full picture. Outsiders see individual observations without the aggregated context. Reports of classified involvement, reports of classified military observation assets being retasked to monitor 3I Atlas add another layer. These reports are unverified. Anonymous sources. No official confirmation. They might be exaggerated or entirely fabricated by media outlets seeking dramatic headlines. But multiple outlets have published similar claims independently. That suggests either coordinated misinformation, which seems unlikely for something this obscure, or actual leaks from within observation or defense communities. If true, retasking classified platforms means 3I Atlas was deemed high enough priority to interrupt other intelligence operations. That goes beyond training. That is operational response. So, we're left balancing two interpretations. On one hand, a legitimate training exercise using a convenient interstellar visitor to validate planetary defense systems. On the other hand, a response to an object exhibiting characteristics significant enough to justify monitoring with every asset available, framed publicly as training to avoid causing concern about something they don't fully understand yet. Both interpretations fit most of the facts. Neither can be definitively proven with available information, and maybe that ambiguity is intentional. What tips the scales toward questioning the training narrative isn't any single element, it is the stacking. The chemical anomalies, plus the unprecedented campaign structure, plus the tight timelines, plus the restricted access, plus the reports of military involvement, plus the specific choice of this object over more representative alternatives. Any one of those is explainable. All of them together create a pattern that feels like more than routine practice. Not conspiracy, not covered up. Just the possibility that planetary defense officials are taking 3i Atlas seriously enough to activate protocols that extend beyond training into actual precautionary monitoring. And if that is true, if this campaign is at least partly driven by genuine uncertainty about what 3i Atlas is, then the question becomes, what have they seen in the data available to them, but not yet publicly released, that justifies treating a harmless object as worthy of this response? Information gaps, facts versus explore that. We need to look at what remains hidden, the data gaps, the embargo periods, the information asymmetries between what professional observers know and what the public sees. Because transparency isn't always immediate in astronomy, and that delay creates space for legitimate questions. We need to be careful here, extremely careful, because this is where evidence ends and speculation begins, and conflating the two destroys credibility. So, let's establish what we know for certain, versus what has been reported through unverifiable channels, versus what is pure conjecture. The distinction matters. It is the difference between asking legitimate questions and promoting conspiracy theories. Here is what is documented. The International Asteroid Warning Network launched an unprecedented observation campaign for 3i Atlas. Multiple professional observatories using some of humanity's most advanced instruments have committed resources to studying this object. The observation data collected so far shows chemical and behavioral characteristics that don't match existing Comet models. All of that is confirmed through official sources, published bulletins, and peer-reviewed or preprint scientific papers. Those are facts. Now, here is what has been reported by media outlets, but remains unverified. Several publications, including the New York Post and various international news services, have stated that NASA activated planetary defense systems in response to 3i Atlas. Some articles reference retasked satellites and classified observation platforms being redirected to monitor the object. These reports cite anonymous sources within aerospace or defense communities. NASA has not publicly confirmed these specific claims. The articles exist. The claims are out there, but their accuracy cannot be independently verified. That is the honest assessment. Let's establish a baseline for what is normal. The United States Space Surveillance Network, operated by the Department of Defense and Space Force, tracks thousands of objects in Earth orbit and beyond. Satellites, space debris, asteroids, comets, and anything that moves through near-Earth space gets catalogued. That is routine space situational awareness. If Space Force weren't tracking 3i Atlas, that would be abnormal. The object passed within 1.8 astronomical units, well within the region military space monitoring covers. So yes, defense assets are observing 3i Atlas. That is not suspicious. That is standard procedure. What would be unusual is retasking. Retasking means redirecting a satellite or telescope from its planned mission to focus on something else. That costs money. It disrupts operational schedules. It requires justification up the command chain. Assets get retasked when something is deemed higher priority than whatever they were previously monitoring. So if reports are accurate that classified platforms were retasked specifically for 3i Atlas, that implies the object was elevated to priority status. But again, we have no official confirmation, just media reports citing sources we can't verify. There is also the question of what classified platforms might mean. Some military satellites have optical or infrared sensors capable of detailed space observation. Originally designed for missile tracking or satellite surveillance, they can also observe asteroids and comets. NASA and the DoD share data routinely. NASA requests military observation assets for planetary defense purposes regularly, so military involvement isn't inherently suspicious. The question is whether the level of involvement for 3i Atlas matches typical cooperation or exceeds it. Without access to classified information, we can't answer that definitively. Data embargoes are another area where normal practice becomes suspicious if context is ignored. In professional astronomy, when a research team is granted telescope time on major instruments like Hubble or JWST, they typically receive a proprietary period, 6 months to a year, where the data is exclusively theirs. This allows them to analyze findings and publish papers without being scooped by other researchers using publicly released data. It is standard. It protects the investment of time and resources teams make in planning observations. So, the fact that some 3I Atlas observation data hasn't been released immediately isn't necessarily suspicious, but some observers have noted delays beyond typical embargo periods. Data that should have become public hasn't appeared in expected archives. Now, that could be administrative, processing delays, researchers still analyzing before release. Nothing nefarious, just slower timelines than expected, or it could be more deliberate. Data held back because it shows something significant that requires careful analysis before public release, or data classified because it was gathered using military assets with classification requirements. We don't know which scenario applies because, by definition, withheld data can't be examined to determine why it is withheld. Let's apply Occam's razor honestly. The simplest explanation is that military assets are tracking 3I Atlas using standard protocols. Some observation data is under typical proprietary embargo, and media outlets are sensationalizing routine procedures because NASA activates defense systems for Comet generates more clicks than NASA observes harmless interstellar object. That is probably accurate for most of what we're seeing. Media loves dramatic framing. Space stories get exaggerated. People misunderstand normal procedures and interpret them as emergency response. That accounts for much of the hype, but not necessarily all of it, because multiple outlets publish similar details about retasked satellites and classified protocols from apparently separate sources. Either they're all citing the same original report, which is possible through media echo chamber effects, or multiple people within relevant communities leaked similar information independently. The latter scenario suggests there might be truth beneath the exaggeration. Not that IORN is preparing for impact. Obviously, but that 3I Atlas received attention from classified observation assets at a level beyond routine tracking. Again, speculation, but not baseless speculation. The problem is unfalsifiability. If activities are classified, they won't be publicly disclosed. If defense satellites were retasked, that information would be restricted. If intelligence agencies are involved in analyzing 3I Atlas data, we wouldn't know through official channels. The only way such information surfaces is through leaks, and leaks are inherently difficult to verify because sources remain anonymous to protect their positions. So, we're left in epistemological limbo, unable to confirm or deny claims about classified involvement. What we can do is evaluate consistency. Do the unverified claims align with other documented facts? The unprecedented ORN campaign is documented. The chemical anomalies are documented. The tight timelines and restricted participation are documented. Those facts establish that 3I Atlas is receiving unusual attention. Reports of classified involvement, if true, would be consistent with that pattern. They wouldn't contradict known facts, they'd extend them. That doesn't prove the reports are accurate. It just means they're not obviously false. And there is the question of motivation. Why would defense or intelligence agencies care about an interstellar comet that poses no collision risk? Several answers exist. 1. They don't care specifically about 3I Atlas, but are participating in the IORN campaign as part of broader planetary defense cooperation. 2. They're testing whether classified observation assets can contribute effectively to civilian planetary defense efforts. 3. They're monitoring 3I Atlas because its anomalous characteristics warrant precautionary observation to ensure we fully understand what it is before it leaves. 4. They've detected something in classified observations that hasn't been publicly released. Each of those explanations is plausible. Each has different implications. Let me be explicit about what I'm not saying. I'm not claiming there is a conspiracy. I'm not suggesting NASA is lying. I'm not implying 3I Atlas is an alien spacecraft being tracked in secret. Those leaps are unwarranted by available evidence. What I'm saying is this: when an interstellar object with unprecedented chemical characteristics triggers an unprecedented IORN campaign with restricted access and tight timelines, and multiple media outlets independently report classified observation assets being involved, and professional astronomers note that expected data releases are delayed, the pattern warrants questions, not conclusions. Questions the scientific method demands skepticism toward both sensational claims and dismissive explanations. Claiming definitively that something extraordinary is happening requires evidence we don't have. But claiming definitively that nothing unusual is happening requires ignoring the documented anomalies and unprecedented response. The intellectually honest position is uncertainty. Acknowledging we don't have complete information, recognizing that both a routine explanation and a something more significant explanation remain possible until additional data resolves ambiguity, and that data might come from an unexpected voice, a researcher whose credibility is simultaneously impeccable and controversial, someone whose scientific credentials are beyond dispute, but whose willingness to consider unconventional hypotheses has made him a polarizing figure, someone who has been analyzing 3I Atlas since its discovery and has gone on record stating that the object represents what he calls a potential black swan event. That researcher is Dr. A.V. Loeb, and whether you trust his interpretations or not, understanding his analysis is essential to evaluating what 3I Atlas might represent. Dr. Abraham A.V. Loeb is the Frank B. Baird Jr. Professor of Science at Harvard University, former chair of Harvard's Astronomy Department, founding director of Harvard's Black Hole Initiative, over 1,000 peered and reviewed papers published, advisor to numerous PhD students, member of the President's Council of Advisors on Science and Technology. By conventional academic metrics, he is one of the most accomplished astrophysicists alive. He is also, depending on perspective, either a visionary willing to ask uncomfortable questions or a scientist who sacrificed rigorous skepticism for public attention. Both assessments contain truth, and the tension between them defines why his voice matters in the 3I Atlas conversation. Loeb first became a household name, at least in households that follow astrophysics, with Oumuamua, the first confirmed interstellar object detected in October 2017, as it was already leaving the solar system. Oumuamua exhibited strange acceleration. Its trajectory showed deviations from what gravity alone would predict. For typical comets, that is explained by outgassing, jets of vapor acting like tiny rocket thrusters, creating non-Zen gravitational acceleration. But Oumuamua showed no visible coma, no gas emissions, no dust tail, nothing that would explain the observed acceleration through standard comet mechanisms. Loeb, along with his postdoc Shmuel Bayerly, published a paper in the Astrophysical Journal Letters proposing that one possible explanation was a light sail, a thin reflective surface pushed by solar radiation pressure, artificially constructed, potentially of technological origin. They didn't claim this was definitely true. They argued it was a hypothesis worth considering alongside natural explanations. The scientific community largely rejected this interpretation, favoring explanations like hydrogen iceberg, outgassing, or non-Zen standard comet behavior. But Loeb's willingness to seriously propose artificial origin made him instantly controversial. To some, he became a hero, a scientist brave enough to consider possibilities others dismissed out of fear of ridicule. Someone who recognized that the search for extraterrestrial intelligence shouldn't be limited to radio signals, but should include looking for artifacts, probes, and technological signatures in objects passing through our solar system. To others, he became a cautionary tale, a brilliant scientist who'd gone too far, proposing speculative ideas without sufficient evidence, potentially damaging public understanding of science by legitimizing fringe theories. Both reactions missed the nuance. Loeb isn't claiming Oumuamua was definitely artificial. He is arguing that we can't definitively rule it out based on available data, and that dismissing the possibility without investigation is itself unscientific. His position is that when you observe something genuinely anomalous, you should consider all explanations that fit the data, including unconventional ones, rather than forcing observations into existing frameworks. That is not pseudoscience. That is intellectual humility about the limits of our knowledge. Now he has turned attention to 3I Atlas, and his analysis focuses on specific technical anomalies. First, the nickel emission. Loeb notes that the spectroscopic signatures don't match natural nickel sublimation from comet surfaces. The wavelengths are consistent with nickel tetracarbonyl or similar compounds which are stable at much lower temperatures than pure nickel. Those compounds are primarily known from industrial chemistry. That doesn't prove artificial origin, but it means the observed emissions are more consistent with certain manufactured materials than with natural cosmic nickel deposits. That is a factual observation about chemical signatures, not wild speculation. Second, the absence of iron. Loeb emphasizes that the nickel-Zen-to-Zen ion ratio in 3I Atlas is inconsistent with any known natural formation process. Supernovae eject nickel and iron together. Stellar nucleosynthesis produces them together. They condense together in protoplanetary disks. Finding nickel without proportional iron violates expected cosmic chemistry. Natural explanations exist, perhaps unknown fractionation processes in exotic stellar environments, but they're speculative. We're essentially inventing new processes to explain what we're seeing rather than admitting we don't understand it yet. The anti-Zan tail phenomenon. Loeb and his colleagues have offered natural explanations for this. Optical effects from differential particle velocities creating the appearance of sunward motion, but they've also noted that the specific geometry and persistence of the feature don't perfectly match simulations of that optical effect. It is close, but not exact, which means either our models are incomplete or there is an additional factor we haven't identified. Loeb uses the term black swan event to describe 3I Atlas. The phrase comes from risk analysis. A black swan is an unpredictable event with massive consequences that seems obvious only in hindsight. The 2008 financial crisis, the 9/11 attacks, the COVID-19 pandemic, events that were theoretically possible but not anticipated and whose occurrence fundamentally changed perspectives. Loeb is suggesting 3I Atlas might be that kind of event, not in terms of physical danger, but in terms of what its true nature might reveal. His Trojan horse analogy is deliberately provocative. In the original Greek myth, the Trojans saw a wooden horse and interpreted it as a gift based on their cultural context. It wasn't, Loeb asks. If an advanced civilization wanted to study our solar system, would we recognize their probe, or would we categorize it as a comet because that fits our existing frameworks? He is not asserting 3I Atlas is artificial. He is questioning whether our classification systems are sophisticated enough to distinguish between natural and artificial objects. If the artificial ones are designed to look natural, the scientific community's response has been measured. Most astronomers studying 3I Atlas haven't publicly endorsed the artificial hypothesis. Many acknowledge the chemical anomalies warrant further study, but argue that jumping to artificial explanations is premature when natural processes we don't fully understand remain unexplored. That is appropriate scientific conservatism. Extraordinary claims require extraordinary evidence. Proposing alien artifacts based on spectroscopic signatures that might have natural explanations we haven't discovered yet is putting the cart before the horse. The importance of Loeb's voice in the Galileo project. But here is why Loeb's voice matters regardless of whether his most provocative suggestions are correct. He is reframing the IORN campaign question. Instead of asking, why use 3I Atlas for training, he is asking, why use an object with these specific anomalies? Because planetary defense training works best with representative scenarios, not edge cases. If IORN wanted to practice cometry, any typical solar system comet would serve that purpose. The fact they chose 3I Atlas specifically, with its nickel emissions, unusual composition, and anomalous features, suggests those characteristics are part of why the campaign exists, not incidental details. That doesn't require accepting artificial origin. It just requires acknowledging that the anomalies themselves justify intensive study. Whether 3I Atlas turns out to be a natural object formed through processes we haven't encountered before, or something else, understanding it expands our knowledge. And if there is even a small possibility it is artificial, the potential significance justifies taking that possibility seriously enough to design observations that could detect technological signatures. That is not believing in alien spacecraft. That is doing due diligence. Loeb founded the Galileo project specifically for this purpose, an initiative to search for technological signatures in space using systematic observation and analysis, looking for artifacts, probes, anything artificial that might be passing through the solar system or in Earth orbit. The project uses the same telescopes and analysis methods as conventional astronomy. The difference is intent, looking not just to classify objects as comets or asteroids, but to determine whether any exhibit characteristics incompatible with natural formation. That is a legitimate scientific program regardless of whether it ever finds anything. And 3I Atlas fits that program perfectly. It is interstellar, so if it were artificial, it could have originated from another stellar system. Its chemical composition doesn't match natural models cleanly. Its behavior exhibits features we haven't seen before. Studying it intensively with open consideration that it might be something other than a natural comet is exactly what the Galileo project was designed to do. So, Loeb's involvement makes sense from his research perspective, independent of whether his interpretations ultimately prove correct. The broader point is this: Loeb forces the question to remain open. Without his voice, 3I Atlas could be easily categorized as an interesting comet with unusual chemistry and studied within conventional frameworks. His presence in the conversation means the artificial hypothesis stays on the table. That doesn't mean it is correct. It means dismissing it requires addressing the evidence rather than ignoring it. And that is healthy for science, even if uncomfortable for scientists who prefer certainty. So as we evaluate what the outbound campaign means, Loeb's analysis provides an essential perspective, not necessarily the right perspective, but one that highlights the gaps between what we're seeing and what existing models predict, whether those gaps represent new natural processes or something genuinely unprecedented. They're real. And the fact that planetary defense networks are responding to an object containing those gaps with unprecedented mobilization suggests somebody, somewhere in the decisions and making chain, is taking the uncertainty seriously. To understand just how seriously, we need to look beyond the public campaign announcement and examine the structure itself. The registration requirements, the mandatory workshop, the observation protocols, the data submission standards, because organizational details reveal priorities, and the priorities embedded in this campaign structure tell us something about what they're actually preparing for, whether it is improving techniques, investigating anomalies, or something that combines both purposes. When you want to understand an organization's true priorities, don't listen to what they say, watch what they do, examine the structures they build, the timelines they impose, the resources they allocate, the restrictions they enforce, because structure reveals intent more honestly than statements ever can. And the structure of the 3I Atlas Ion campaign, when examined closely, tells a story that is more complex than a simple training exercise. Start with the timeline. October 20, Jan 1st, bulletin published. November 7th, registration closes. That is 17 days. For context, most astronomical campaigns announce months in advance. Professional observatories schedule telescope time 6 to 12 months ahead. Researchers need to arrange funding, coordinate travel, prepare proposals. Yet, Yorn demanded commitment within 2.5 weeks. Why? The official answer is time sensitivity. 3I Atlas is moving fast. Visibility is limited. The opportunity won't last. All true, but also true. They announced the campaign the instant solar conjunction ended, suggesting the decision was made earlier and held until observation became possible again. That means the campaign was planned during conjunction, when direct observation was impossible, based on data gathered before conjunction ended. Data showing the chemical anomalies, the nickel emissions, the unusual composition. So, the decision to mobilize wasn't made after discovering something new during early campaign observations. It was made proactively, based on known anomalies. The campaign is a response to what they already knew 3I Atlas was, not a discovery process to learn what it might be. That is a subtle but significant distinction. November 10th. Mandatory workshop, not optional attendance, not recommended participation. Mandatory. If you didn't register by November 7th and attend on November 10th, you're excluded from the official campaign. Astronomy doesn't usually work this way. Scientific collaboration is typically open. Methods are published, techniques are shared. Anyone with appropriate equipment can observe and contribute data. But this campaign created barriers, prerequisites, controlled access. What could justify that? One answer: standardization. If you're trying to aggregate measurements from dozens of observatories worldwide, you need everyone using compatible methodologies. Position measurements must reference the same coordinate systems. Brightness measurements must account for instrumental differences. Timestamps must synchronize precisely. The workshop could be teaching those standardization protocols, ensuring data quality through consistent practice. That is entirely reasonable. It is how you build reliable datasets from diverse sources. But it also means something else. It means knowledge stratification. After November 10th, there are two groups: those who attended the workshop and know what they're looking for, and those who didn't and are observing blind. The workshop content hasn't been published. We don't know what was taught, what specific techniques were emphasized, what particular features observers were told to prioritize. That information remains internal to campaign participants, which creates an information asymmetry. Insiders see the full picture, outsiders see fragments. The citizen scientist invitation is genuinely remarkable. IORN campaigns are typically professional affairs. National space agencies, university observatories, government funded facilities. Opening this to amateur astronomers with backyard telescopes breaks precedent. It suggests they need coverage, maximum geographic distribution, as many eyes on 3I Atlas as possible from as many locations as possible, capturing data under diverse atmospheric and observational conditions. Volume matters more than individual instrument quality. Why would volume matter for training? Because you're testing coordination at scale, ensuring data aggregation systems can handle inputs from hundreds of sources. validating that international communication channels work efficiently under load. That fits the training narrative, but volume also matters for verification. If you need consensus, if you need to confirm observations independently across multiple platforms, so no single source can be dismissed as instrumental error or measurement artifact. If you need to build a dataset robust enough that findings become undeniable, regardless of how unusual they might be. The pressure of finality and data protocols. The observation window runs November 20 Gen 7th through January 20 Gen 7th, 2 months precisely. That captures 3I Atlas during its optimal post-Gen perihelion phase. After October 20 Gen 9th, the object is moving away from the Sun, but still bright enough for detailed observation through December. By January, it dims significantly. By late January, it approaches the threshold where even large professional telescopes struggle to detect it. The campaign window represents the last clear look humanity will ever get. After January 3I Atlas fades into interstellar space permanently. Everything we learn must be learned in this window, or it remains unknown forever. That finality creates pressure, not the artificial pressure of imposed deadlines, but the genuine pressure of opportunity cost. Every hour not observing is an hour lost permanently. That changes decisions and making. It justifies resource allocation that might seem excessive under normal circumstances, because there is no let's wait and observe it more carefully next time. This is the only time. And if there is any possibility that 3I Atlas represents something significant, missing that discovery because we didn't observe intensively enough would be a failure we'd regret for generations. The data protocols are revealing. Astrometry must be submitted in standardized formats to the Minor Planet Center, real-time time aggregation. Not the typical astronomical workflow where data is collected, analyzed over months, peered and reviewed, and published eventually. This is operational tempo, continuous data flow, immediate integration. The Minor Planet Center processes inputs as they arrive, updating 3I Atlas's orbital parameters continuously as new measurements refine calculations. That is how you track a threat. That is impact scenario procedure applied to an object that poses no impact threat. Now, that makes sense for training. If you're simulating planetary defense response, you practice operational tempo even when there is no actual emergency. You want coordination systems tested under realistic speed pressure, so real-time time aggregation fits the training narrative, but it also means something else. It means only the Minor Planet Center and campaign coordinators see the complete dataset. Individual observers contribute measurements without knowing what the aggregated picture shows, without seeing how their data combines with everyone else's to reveal patterns or changes that might not be visible in isolated observations. That is information asymmetry again. Participants contribute, coordinators integrate. Findings get released eventually, presumably after the campaign concludes and analysis is complete. But during the campaign, during those 2 critical months when 3I Atlas is observable, only the inner circle knows what the full dataset is revealing. Maybe that is necessary for operational efficiency. Maybe consolidating analysis prevents premature conclusions based on incomplete data. Or maybe it ensures that if something unexpected appears in the observations, it can be evaluated privately before public disclosure. Professional observatories worldwide have committed extraordinary resources. James Webb Space Telescope time, which costs approximately $30,000 per hour of observation. Hubble Space Telescope, similarly expensive. Keck Observatory, very large telescope. European Space Agency's Mars Express. These aren't minor commitments. This is millions of dollars in telescope time and personnel costs. For training, possibly. That is expensive training, but arguably worthwhile for planetary defense readiness. But the expense also signals priority. You don't allocate millions in resources for routine scientific curiosity. You allocate that when something matters enough to justify the cost. Compared to previous interstellar objects, the contrast is stark. Oumuamua was observed opportunistically. Individual astronomers pointed telescopes at it when they could. No coordinated campaign, no formal structure, just decentralized scientific interest. Borisov received more attention, with multiple observatories tracking it systematically. But still no ION involvement, no registration, no mandatory workshops. Just open collaboration. 3I Atlas is receiving treatment that mirrors potentially hazardous near-Earth Earth object protocols. The same data sharing requirements, the same operational tempo. That framework exists for impact scenarios, for objects that might threaten Earth. Using it for 3I Atlas means either they're practicing those protocols on a convenient, harmless target, or they're applying impact scenario procedures to an object that warrants that level of scrutiny for reasons beyond training. Both interpretations fit, both explain most observations, and maybe both are simultaneously true. Maybe this is training that uses real anomalous data to make the exercise as realistic as possible. Training that becomes investigation when the training target turns out to be more interesting than expected. What the structure doesn't tell us is what they expect to find, what hypothesis they're testing, what specific question the campaign is designed to answer. Is it purely methodological? Can we track difficult comets accurately? Or is it empirical? What is 3i Atlas actually made of? And does its composition match any known natural formation process? Or is it even deeper? Does this object exhibit any characteristics inconsistent with natural origin that would warrant considering alternative explanations? The structure accommodates all those questions. It is flexible enough to serve as training, investigation, or both simultaneously. And that flexibility might be intentional, because if you're mobilizing international resources to study something genuinely uncertain, something that might be completely mundane or might be unprecedented, you don't announce it as a world-changing investigation. You frame it as routine preparation. You use language that is procedurally accurate, even if it doesn't capture the full significance. You let the data speak for itself once the campaign concludes, and that is where we are, watching a coordinated international campaign track an interstellar object with unprecedented characteristics using planetary defense protocols designed for threat response. While being told it is training, knowing that the training explanation is plausible and well-designed supported, also knowing that the anomalies are real and significant enough to justify intensive study independent of training value, unable to conclusively determine which motivation dominates because the campaign structure supports both. So perhaps the right question isn't, is this training or investigation? Perhaps it is, what does planetary defense actually require? Because if defending Earth means being ready for the unexpected, for scenarios that don't fit models, for objects that challenge assumptions, then training on an anomalous interstellar visitor makes perfect strategic sense. You're not preparing for typical threats, you're preparing for the threats you can't predict, the ones that appear without warning and demand rapid, coordinated response despite uncertainty. And from that perspective, 3i Atlas isn't just a convenient training target. It is exactly the kind of challenge planetary defense needs to be ready for. Planetary defense sounds like science fiction terminology, but it is operational reality. We've moved beyond theoretical discussions into practical implementation, and understanding what planetary defense actually requires, beyond the physics of deflection, reveals why 3i Atlas matters, regardless of whether it is natural or represents something else. Because the hardest part of planetary defense isn't moving asteroids. The hardest part is everything that comes before that capability can be deployed. Consider the full operational sequence from detection to deflection. Step 1. Detection. Telescopes must scan the sky systematically, identifying objects that weren't there previously or tracking known objects whose orbits might intersect Earth's path. That requires dedicated survey programs, automated detection algorithms, and global coverage to ensure nothing slips through observational gaps. We've gotten better at this. Programs like Panzian Stars and the upcoming Vera C. Rubin Observatory dramatically improve detection capabilities, but we still miss objects, especially those approaching from the sun's direction, where solar glare blinds telescopes. Step 2. Tracking. Once detected, the object must be observed repeatedly to establish its orbit with precision. This is where astrometry becomes critical. Initial observations give a rough trajectory. But rough isn't sufficient. You need kilometer-level precision in position measurements to calculate whether an object will actually impact Earth or pass safely by. For asteroids, this takes weeks of observation. For comets with their unpredictable outgassing, it can take months. And if an object is discovered with only weeks or months until potential impact, you're racing the clock to get measurements accurate enough to make decisions. Step 3. Characterization. Understanding the object's physical properties, size, shape, rotation, composition, structural integrity. Is it solid rock, a loosely bound rubble pile, metallic, icy? Those characteristics determine which deflection strategies might work. Kinetic impactors work well on solid objects. Gravity tractors work better on rubble piles where kinetic impact might shatter the target into multiple dangerous fragments. You need to know what you're dealing with before planning intervention. Step 4. Threat assessment. Calculating impact probability and potential damage. Where would it hit? What is the likely impact energy? How large is the affected area? that assessment determines priority level. A small object hitting the ocean causes minimal damage. A large object hitting a populated region causes catastrophic casualties. Resources get allocated based on threat severity, but threat assessment requires accurate data from previous steps. Garbage in, garbage out. If your position measurements are wrong, your impact predictions are wrong, and you might either over-ZAN respond to false threats or under-ZAN respond to real ones. Step 5. Decision ZAN making. Who decides whether to attempt deflection? That is not a technical question. It is political, legal, and ethical. If an asteroid will hit Kazakhstan, does Kazakhstan get to decide on deflection? What if deflection changes the impact point to Canada? Who is liable? Who pays for the mission? The United Nations has frameworks through IORN and the Space Mission Planning Advisory Group, but those frameworks have never been tested operationally. The 3I Atlas campaign is in some ways testing whether international consensus can be reached quickly enough to matter. Step 6. Mission planning. Designing the deflection spacecraft. Calculating launch windows. Determining intercept trajectories. This takes years under ideal conditions. DART took nearly 5 years from congressional authorization to launch, and DART targeted Dimorphos, an object we tracked for decades with well-ZAN established orbital parameters. Deflecting an object discovered with minimal warning compresses that timeline to months or weeks. That might not be physically possible depending on where the object is and where Earth is in its orbit when detection occurs. Step 7. Execution. Building, launching, and navigating the deflection mission. Ensuring the spacecraft hits the target with precise timing and velocity. Confirming the deflection succeeded and the object's new trajectory is safe. Then monitoring to ensure no unexpected fragmentation occurred that created multiple smaller but still dangerous objects. Each step has failure modes. Each step requires capabilities that must be validated before facing real scenarios. That is the planetary defense equation. 7 complex steps, each dependent on previous steps, each requiring international cooperation, each constrained by physics and time. And the entire system fails if any single step fails. You can't deflect an object you didn't detect. You can't plan a mission without accurate tracking. You can't execute deflection without international consensus and funding. The chain is only as strong as its weakest link. Now apply that framework to Comet specifically, and complexity multiplies. Asteroids follow predictable gravitational paths. Comets don't. Outgassing creates non-ZAN gravitational acceleration. Jets of vapor act like tiny rocket engines, subtly changing trajectory in ways that depend on where gas vents are located on the nucleus. How fast the nucleus rotates, how solar heating varies with distance from the sun. All of those factors are difficult to predict, which means comet trajectories have inherent uncertainty that asteroid trajectories don't. That uncertainty cascades through the planetary defense equation. If you can't predict trajectory accurately, threat assessment becomes uncertain. If threat assessment is uncertain, decision ZAN making becomes paralyzed by ambiguity. Do you launch an expensive deflection mission when you're only 70% certain impact will occur? What if that 70% confidence comes from tracking measurements that have systematic errors you don't fully understand? The margin for error tightens dramatically with comets compared to asteroids, and comets give less warning. Many comets come from the Oort cloud, the distant spherical shell of icy bodies surrounding the solar system far beyond Pluto. Objects can be gravitationally perturbed from the Oort cloud, falling sunward on trajectories we don't see until they're already approaching the inner solar system. By the time detection occurs, you might have months, not years. The entire planetary defense timeline compresses. Detection to deflection execution must happen faster than the system was designed to operate. That is the nightmare scenario planetary defense officials lose sleep over. Not a well-ZAN tracked asteroid we've monitored for decades. A comet appearing from the outer solar system with minimal warning, exhibiting unpredictable trajectory changes, discovered too late for careful characterization, requiring international consensus and mission execution under time pressure that allows no delays. That scenario is statistically unlikely, but not impossible, and preparing for it requires practicing with objects that simulate those conditions. From this perspective, 3I Atlas genuinely is ideal training. It is a comet with difficult astrometry. It is moving fast, creating compressed observation windows. It is compositionally unknown, forcing characterization without prior knowledge. It appeared from interstellar space, simulating unexpected arrival, and critically, it is harmless, so mistakes cost nothing but learning. Every challenge planetary defense might face with a real comet threat exists with 3i Atlas, except actual danger. That is valuable simulation. But here is the deeper question. If this is training, what scenario are they training for? The stated purpose is improving astrometry techniques. Fair enough, but the scope of mobilization exceeds what astrometry practice alone requires. The involvement of multiple space agencies, the real-time data aggregation, the international coordination protocols. That is full spectrum planetary defense activation. They're not just practicing measurements, they're practicing the entire response framework: detection, tracking, characterization, threat assessment, international coordination, data sharing, consensus building, everything except mission planning and execution, because those steps only activate if there is an actual threat to deflect. So maybe the scenario they're training for isn't, can we measure comets accurately? Maybe it is, can we coordinate globally on a compressed timeline when facing an object we don't fully understand? That is a different question with different implications. It means the training value isn't technical, it is organizational. Testing whether international cooperation works under pressure, whether data sharing happens quickly enough, whether consensus can be reached when uncertainty is high and time is limited. And if that is the real test, then the anomalous characteristics of 3i Atlas aren't incidental, they're central. Because uncertainty is what makes coordination difficult. If everyone agrees the object is a normal comet, coordination is easy. If the object exhibits characteristics no one can explain, if researchers disagree on interpretation, if data suggests multiple incompatible scenarios, coordination becomes challenging. Trust breaks down. Nations hesitate to commit resources based on uncertain threat assessments. That is when international frameworks either prove functional or collapse under stress. That would explain why they chose 3i Atlas specifically. Not because it is a typical comet, but because it is an atypical one. One that forces participants to coordinate despite uncertainty, to reach consensus despite ambiguity, to function effectively even when they don't fully understand what they're observing. That is the real test of planetary defense readiness. Not technical capability, but institutional resilience under conditions that resist easy answers. And if we're correct about that interpretation, then what happens over the next 2 months becomes revealing. Not just what they discover about 3i Atlas's composition and trajectory, but what they demonstrate about international cooperation. Whether data sharing happens transparently, whether findings get released openly or disappear behind proprietary embargoes, whether consensus emerges naturally or fractures along institutional or national lines. The meta-level test is whether humanity can function as a cooperative species when facing cosmic uncertainty. That is what the Iron Dawn campaign might really be testing. And the results matter not just for 3i Atlas, but for every future scenario where we face something we don't immediately understand but must respond to anyway, because the universe doesn't owe us simple explanations. Sometimes the answer is, we don't know yet. And what we do during that period of not knowing reveals more about our readiness than any technical capability ever could. So, as we watch this campaign unfold in real time, as observations accumulate and data gets analyzed, the question to keep asking isn't just, what is 3i Atlas? It is, are we ready for whatever it might be? And more broadly, are we ready for the next cosmic surprise, whatever form it takes? Right now, as you're watching this, 3i Atlas is out there, moving away from the Sun at 210,000 kilometers per hour. Every hour, it travels another 210,000 kilometers deeper into space. Every day, another 5 million kilometers. By the time this video ends, it will be measurably farther from us than when you started watching. That is not metaphor. That is literal. This object is leaving, and everything we're about to learn will be learned while it is still observable, or it won't be learned at all. The timeline is compressed and immediate. Today is October 29th. Perihelion just happened. 3i Atlas is now on the outbound leg of its hyperbolic trajectory, in 9 days. November 7th, registration closes for campaign participation. That deadline isn't arbitrary. It is the cutoff point where logistical coordination becomes impossible. Anyone wanting to contribute observations officially must commit within the next week. After November 7th, the participant list is locked. 3 days after that, November 10th, the mandatory workshop occurs. We don't know the content, we don't know what techniques will be taught or what specific observational priorities will be emphasized. That information exists somewhere in planning documents and training materials, but it hasn't been made public. What we do know is that whatever gets taught in that workshop will shape how observations are conducted throughout the campaign. It will determine what data gets prioritized, how measurements get standardized, What questions observers are trying to answer. The workshop is the lens through which hundreds of telescopes will view 3i Atlas for the following 2 months. 17 days after the workshop, November 27th, the official campaign begins. That is when coordinated observations start in earnest. That is when the real Zen time data aggregation activates. That is when every participating observatory, from professional facilities to citizen astronomers with backyard instruments, starts submitting astrometry measurements to the Minor Planet Center for integration into the growing dataset. And that is when we, the public watching from outside, start seeing whether preliminary findings trickle out through scientific conferences, preprint servers, or media coverage. The observation window spans December and January. December represents peak opportunity. 3i Atlas will still be bright enough for detailed spectroscopy. Professional observatories will be conducting intensive observations, capturing data on composition, brightness variations, structural features, anything visible through their instruments. This is when followed Zen-up analysis of the nickel emissions happens, when researchers look for ion signatures with greater sensitivity, when they search for other chemical anomalies that preliminary observations might have missed. January represents the closing window. As 3i Atlas dims, larger telescopes become necessary for continued observation. Smaller instruments lose the object in background noise. By late January, only the most powerful facilities will still have clear detection. The campaign's official end date, January 27th, marks the point where coordinated observation becomes impractical because the object has faded below detection thresholds for most participating instruments. After that date, 3i Atlas effectively disappears. It continues existing, continues traveling through space, but it is too faint and too distant for any Earth-Jan-based telescope to see. That finality matters psychologically. This isn't, we'll observe more thoroughly next apparition. There is no next apparition. This is one pass, one chance, one opportunity that ends definitively on January 27th. Everything learned must be learned by then. Everything missed remains unknown permanently. That creates urgency even if there is no physical threat, because the cost of incomplete observation is permanent ignorance. So what should we be watching for? What data points would be significant? First, orbital refinements. If 3i Atlas exhibits non-Zen gravitational acceleration beyond what can be explained by standard outgassing models, that deepens the mystery. It suggests either unusual gas emission patterns, unusual surface properties, or mechanisms we don't understand. Researchers will be tracking position with extreme precision, looking for any trajectory deviations from purely gravitational paths. Second, spectroscopic updates. More detailed analysis of the nickel emissions. Whether iron appears in later observations, now that instruments know what to look for. Whether other elements show unusual abundances or unexpected chemical compounds. Spectroscopy is how we determine composition, and composition is how we understand formation history. Anomalies in composition mean anomalies in origin that require explanation. Third, brightness fluctuations. If 3i Atlas brightens or dims unexpectedly, independent of distance from the Sun, that indicates something changing on the surface. Perhaps rotation exposing different regions to sunlight. Perhaps active regions where outgassing suddenly increases. Perhaps structural changes or fragmentation events. Monitoring brightness over time reveals dynamic processes that static composition measurements can't capture. Fourth, structural observations. High-Zen resolution imaging looking for shape details, surface features, fragmentation, changes in the coma structure or anti-Zen tail configuration. The more detailed the images, the more we can infer about the physical object hiding behind the gas and dust. Hubble and JWST observations will be critical here, because they have resolution no ground-Zen-based telescope can match. Now, what would constitute red flags versus expected results? Expected results would be refined orbital parameters confirming hyperbolic trajectory, better composition measurements resolving current anomalies through natural explanations, successful international data coordination demonstrating planetary defense readiness, and published papers by spring 2020 Zen 6 detailing findings. That is the baseline success scenario. Training accomplished, science advanced, preparedness validated. Red flags would be sudden orbital changes inconsistent with comet behavior, continued absence of iron despite intensive observation, discovery of electromagnetic emissions or structured signals, unexplained data embargoes extending beyond typical proprietary periods, or simply silence. If the campaign concludes January 27th, and no findings emerge by mid-Gen 2020 Gen 6, that would raise questions. Scientific papers take time, yes, but preliminary results usually appear quickly through conferences and preprint servers. Extended silence after intensive observation would be unusual. For those outside the official campaign, observation is still possible. Citizen scientists with 8-inch or larger telescopes in the southern hemisphere have best viewing during December. 3i Atlas will be a faint fuzzy patch, magnitude 10 to 11, not easy, but detectable with proper equipment and technique. Photographing it won't reveal composition or detailed structure, but it provides the visceral experience of seeing an interstellar visitor with your own eyes through your own instrument. That connects you personally to this cosmic event in ways that reading reports never can. Even without telescopes, following along is straightforward. The Minor Planet Center publishes updated orbital elements regularly. Amateur astronomy forums, especially on Reddit is RI Space and RI Astronomy, will have ongoing discussions as news emerges. Professional astronomers often share preliminary findings on social media before formal publication. The Astronomer's Telegram and the Arxiv preprint server are where breaking astronomical discoveries appear first, sometimes days or weeks before peer-reviewed journals. Dr. Loeb and researchers involved with the Galileo project will likely publish analysis rapidly. Loeb has been consistently vocal about 3i Atlas since its discovery, and his pattern is to share findings through preprints and public statements before waiting for slow peer-gen review processes. Whether you trust his interpretations or not, he is reliably transparent about data and methodology. Following his publications provides one perspective on what the observations are revealing. NASA's Planetary-Defense Coordination Office website will likely provide updates, though possibly less frequently than independent researchers. Official channels move slowly, filtered through communication offices and approval processes. But when they do release statements, they carry institutional authority that individual researcher claims don't. Balancing rapid independent reports against slower official statements gives a fuller picture than relying on either alone. Major science journalism outlets will cover significant developments. Scientific American, Nature News, Science Magazine, Space.com. These publications have reporters embedded in the astronomy community who break stories as they emerge. Quality varies and headlines often sensationalize, but the underlying reporting usually includes interviews with researchers and links to primary sources. Following those outlets ensures you don't miss major announcements. The metagen story to watch is transparency. Does data flow openly? Do findings get shared promptly? Is there clear communication about what is being discovered and what remains uncertain? Or do barriers appear? Information gaps, delayed releases, contradictory statements. Those patterns tell their own story separate from the specific scientific findings. Because how institutions communicate during this campaign reveals their priorities and their comfort level with public scrutiny. And after January 27th, after the campaign officially ends, attention shifts to analysis and publication. Raw data must be processed. Observations must be compared against models. Anomalies must be investigated. Peer review must occur. That takes months minimum, potentially a year or more for comprehensive studies, so the immediate aftermath might be quiet. Don't interpret silence as a covered up. Interpret it as science proceeding at its normal, frustratingly slow pace. But by summer 2020 Gen 6, we should have preliminary papers, conference presentations, reviews, and synthesis articles. That is when the fuller picture emerges, when researchers who've spent months analyzing data present their conclusions, when debates occur in academic settings about interpretation, when consensus begins forming, or doesn't around what 3i Atlas actually was and what it meant, that future analysis will happen regardless. It is built into how science works. What is unique about this moment right now is that we're at the beginning. The campaign is launching. The observations are starting. The data doesn't exist yet. We're watching knowledge being created in real time, which is rare and valuable. Most science reaches public awareness only after completion, after papers are published and findings are established. This time we're seeing the process unfold while the outcome remains uncertain. That uncertainty is uncomfortable but important, because this is how discovery actually works, not through sudden revelation, but through gradual accumulation of data that slowly resolves ambiguity, and sometimes rarely through discovering that ambiguity doesn't resolve, that what you're seeing genuinely doesn't fit existing frameworks and requires expanding those frameworks to accommodate new reality. Whether that happens with 3i Atlas remains unknown, but the next 2 months will determine the answer, and we'll be watching. Step back, pull perspective out from the specifics of 3i Atlas, away from the chemical anomalies and campaign structures and data embargoes, and look at what we're actually witnessing. Because this moment represents something larger than one interstellar comet, this is humanity's transition into being an interstellar Xan-aware civilization. We're learning in real time how to function in a universe where objects from other stellar systems pass through regularly, where the solar system isn't isolated, but is constantly receiving visitors from elsewhere. And that transition, regardless of what any specific visitor turns out to be, fundamentally changes our relationship with the cosmos. Oumuamua was the Wake Jan-up call, October 2017. An object moving through the inner solar system on a hyperbolic trajectory, definitively not bound to the Sun, confirmed through detailed observation to be interstellar in origin, the first one we'd ever detected. It caught us unprepared. Telescopes weren't designed to track objects moving that fast. Observation protocols weren't optimized for hyperbolic visitors. By the time we realized what we were seeing, Oumuamua was already leaving, and we scrambled to gather whatever data we could before it disappeared forever. Borisov was the confirmation, September 2019. Another interstellar visitor, this one clearly a comet based on its visible coma and tail. We had more time with Borisov, better observations, more detailed spectroscopy. It showed us that interstellar objects aren't impossibly rare anomalies. They're part of the cosmic background, things drifting through the galaxy that occasionally intersect our solar system's path as we orbit through the Milky Way. Now, 3I Atlas, the third confirmed interstellar object, and critically, the first one where we had institutional frameworks ready, where planetary defense networks could activate, where international coordination could occur systematically rather than frantically. This is what prepared response looks like. Not perfect, not without questions, but organized, coordinated, systematic. That represents progress from the chaos of Oumuamua's discovery to the structured campaign for 3I Atlas. And this is just the beginning. The Vera C. Rubin Observatory, beginning operations now in late 2020 Gen 5, will revolutionize detection. It is designed to photograph the entire visible sky every few nights with sensitivity, far exceeding previous surveys. Astronomers estimate Rubin will detect dozens, possibly hundreds of interstellar objects over the next decade, objects that have been passing through the solar system for millennia. But we lacked the technology to see. We're about to go from interstellar visitors being rare curiosities to interstellar visitors being regular occurrences we catalogue routinely. That changes everything, because currently, each interstellar detection is major news, international coordination, intensive observation, maximum scientific effort. But when we're detecting multiple interstellar objects yearly, that level of response becomes unsustainable. We'll need triage systems, criteria for determining which visitors warrant intensive study, and which get catalogued with basic observations. That is what the 3I Atlas campaign might really be teaching us. How to decide what matters, how to coordinate efficiently without mobilizing every available resource for every detection. But it also raises the statistical question that makes some scientists uncomfortable and others fascinated. If interstellar objects are common, if hundreds or thousands pass through the solar system annually, but we only detect the largest and brightest, what is the probability that at least one of them is artificial? Not a naturally formed comet or asteroid, but a technological artifact. A probe, spacecraft, whatever form advanced civilizations might use for exploration. The math isn't crazy. Our galaxy contains approximately 300 billion stars. If even a tiny fraction of stellar systems produce technological civilizations at some point in their history, that is millions of civilizations. Not all existing simultaneously, because stellar lifetimes span billions of years, but cumulatively over galactic history, millions. If even a tiny fraction of those civilizations send probes or artifacts into interstellar space, that is thousands of objects potentially drifting through the galaxy. Compare that to natural interstellar objects which number in the billions. And yes, natural vastly outnumbers artificial, but artificial isn't zero. It is small but non-Xan zero, and small but non-Xan zero is exactly the kind of probability space we should be prepared to encounter. This is where planetary defense and SETI converge. The search for extraterrestrial intelligence traditionally focused on radio signals, intentional communications broadcast from civilizations trying to make contact. But if technological species send probes rather than broadcasts, if exploration is physical rather than electromagnetic, then detection becomes the same challenge as planetary defense, finding and tracking objects moving through space. The telescopes are identical, the observation techniques are identical. The difference is interpretation. Is this object a rock or an artifact? Natural or artificial? And increasingly, researchers recognize that distinction might not be obvious. If a civilization wanted to explore stellar systems, would they send obviously artificial spacecraft, or would they design probes to mimic natural objects, allowing undetected observation without triggering a response from any inhabitants? Stealth isn't about malevolence. It is about not contaminating observations. An anthropologist studying isolated tribes tries to observe without influencing behavior. Extraterrestrial anthropologists might apply the same principle, which means the artificial objects, if they exist, might be specifically designed to look natural, and we'd categorize them as comets or asteroids because that is what our classification systems expect to see. That is why Loeb's Trojan horse analogy resonates despite making many scientists uncomfortable. Not because it is likely, but because it is unfalsifiable without careful investigation. You can't distinguish between a natural object and an artificial object designed to appear natural without looking for technological signatures specifically. And if you're not looking, if you assume natural origin by default, you'll never find the exceptions. The only way to rule out artificial origin definitively is to look for it systematically and not find it. Dismissing the possibility without investigation doesn't prove natural origin, it just proves you didn't look. That doesn't mean assuming everything is artificial. That is equally unscientific. The correct approach is agnostic investigation. Observe thoroughly. Analyze carefully. Look for characteristics that would distinguish artificial from natural emission patterns, structural features, trajectory changes inconsistent with gravitational and outgassing forces, electromagnetic signals, anything that would require technology to explain. If you find nothing, tentatively classify as natural, while acknowledging you might have missed something. If you find anomalies, investigate further until a natural or artificial explanation clearly fits. That is the only scientifically responsible approach. And that is what makes the 3I Atlas campaign significant regardless of outcome, because the observation intensity, the data quality, the international coordination, that represents our best attempt yet to thoroughly characterize an interstellar visitor, whether it is natural or artificial. We'll learn more about it than we learned about Oumuamua or Borisov. We'll expand our database of interstellar object characteristics, and if it is natural, that database helps us understand what natural looks like, making future artificial detection easier by establishing a baseline. If it is artificial, that is obviously paradigm shifting. Either outcome advances understanding. There is also the philosophical dimension. The fact that we can detect interstellar objects, that we can mobilize international resources to study them, that we can coordinate across political and cultural boundaries in pursuit of knowledge. That says something about our species. It is easy to focus on humanity's divisions, conflicts, failures of cooperation, but space science represents the opposite. Scientists worldwide collaborating because curiosity transcends nationality, because understanding the universe matters enough to overcome the barriers that fragment us in other contexts. That is worth acknowledging. The IORD campaign, whatever its ultimate findings, demonstrates that capability. Observatories on every continent contributing data, governments sharing resources, researchers publishing openly. That is functional global cooperation. Imperfect, yes, complicated by bureaucracy and communication challenges, certainly, but functional, and if we can coordinate effectively on 3I Atlas despite its anomalies and uncertainties, that proves we can coordinate on future challenges. Asteroid deflection. Comet monitoring. Whatever cosmic surprises emerge from improved detection capabilities, which brings us to the responsibility question. We now have the technology to detect interstellar visitors. We have the capability to study them intensively. We're developing infrastructure to track and potentially interact with objects passing through our stellar system. That means we can no longer claim ignorance. If a future interstellar object poses a genuine threat, we won't have the excuse that we didn't see it coming. And if a future object shows clear evidence of artificial origin, we won't have the excuse that we weren't looking. 3I Atlas is teaching us to look, to coordinate, to take seriously the possibility that the universe contains surprises. That is the bigger picture. This isn't just about one comet with strange chemistry. This is about humanity growing up cosmically, learning that the solar system isn't isolated, learning that visitors arrive from elsewhere and will continue arriving, learning that we must be ready for scenarios we haven't encountered yet, because the universe doesn't limit itself to what we've already imagined. That maturation process is ongoing. And 3I iAtlas represents one chapter in that longer story. So, when the campaign concludes in late January, when papers get published in 2020 Gen 6, when findings emerge about composition and structure, and whether the anomalies have natural explanations, remember the context. Whatever we learn about 3iAtlas specifically, we're also learning how to be the kind of civilization that can encounter the unexpected without panic or denial, that can investigate thoroughly without predetermined conclusions, that can coordinate globally despite differences. Those lessons matter at least as much as any specific scientific discovery. And maybe that is the ultimate answer to why the International Asteroid Warning Network activated for a harmless interstellar comet. Not because 3iAtlas is dangerous, but because it is educational, because preparation isn't about responding to current threats, it is about being ready for the threats you haven't encountered yet. The ones that appear without warning and demand response despite uncertainty. The ones that test whether your systems work under conditions they were never specifically designed for. 3iAtlas is that test, and we're taking it seriously because the stakes not of this object but of being unprepared for future objects justify the effort. That is what makes this moment worth paying attention to. Not because we know something extraordinary is happening, but because we're positioned to discover whether something extraordinary is happening, and that possibility, the openness to discovery, is what drives science forward. So, where does that leave us? We started with a question: why does the International Asteroid Warning Network activate unprecedented observation protocols for 3iAtlas, an interstellar comet that poses zero collision risk to Earth? We've explored answers: training exercise to validate planetary defense systems, scientific opportunity to study an anomalous interstellar visitor, precautionary monitoring of an object exhibiting characteristics we don't fully understand, response to chemical signatures inconsistent with known natural comet composition. Each explanation has supporting evidence, each has gaps, and perhaps the honest answer is that all of them are partially true. Here is what we know with certainty. 3iAtlas is real. Its hyperbolic trajectory confirms interstellar origin. Its chemical composition, particularly the nickel emissions without corresponding iron, doesn't match standard comet models. Its anti-Zan tail phenomenon hasn't been observed with this clarity in solar system comets. The ion campaign is unprecedented in structure and scope for an interstellar object. Global observatories are committing millions in resources to intensive 2-month observation. All of that is documented, verified through multiple independent sources. Not speculation, but fact. Here is what we don't know: why this object specifically triggered this response. Why the campaign structure includes restricted access and mandatory workshops. What is being taught in those workshops that requires controlled participation. Whether classified observation assets are involved beyond routine tracking. What the full dataset reveals to campaign coordinators that individual observers don't see. Whether the nickel emissions have natural explanations we haven't discovered or represent something genuinely unprecedented. And critically, what findings will emerge when analysis concludes and papers get published in 2020 Gen 6. Multiple perspectives remain valid. If you believe this is responsible planetary defense training using a convenient interstellar visitor, you're supported by substantial evidence. The campaign structure mirrors preparedness exercises. The stated objectives align with legitimate strategic planning. The investment level, while high, is justifiable for validating systems will depend on during actual threats. That is a reasonable, well-grounded interpretation. If you believe something more significant is occurring, that the anomalies warrant investigation beyond routine training, that the response level indicates genuine uncertainty about what 3iAtlas represents, you're also supported by evidence. The chemical inconsistencies are real. The unprecedented campaign activation breaks established patterns. The timing and intensity suggest priorities beyond what typical training requires. That is equally reasonable and equally grounded. Both can be true simultaneously. Training that uses real anomalous data becomes investigation when the training target exhibits characteristics demanding serious study. The categories aren't mutually exclusive, and perhaps that ambiguity is healthy. Perhaps certainty at this stage would mean we're not asking enough questions, or we're accepting easy answers to complex situations. What makes this different from typical space mysteries is timing. This isn't historical analysis of events long past. This is happening now. November 7th is 8 days away. Registration closes November 10th. Mandatory workshop November 20 Gen 7th. Campaign begins officially. Between now and January 20 Gen 7, 2020 Gen 6, we'll have answers, or at least more data. 3iAtlas won't remain mysterious indefinitely. Either the observations resolve anomalies through natural explanations, or they deepen mysteries further. Either way, we'll know more in 3 months than we know today. That is why you need to stay engaged. Subscribe to this channel immediately if you haven't already, because I'll be covering every significant development, workshop details if they leak, observation findings as they emerge through preprint servers and scientific conferences, analysis of published data updates through December as brightness measurements and spectroscopic studies accumulate, coverage of the January conclusion and immediate aftermath. This is a continuing story, and I'm committed to following it through completion. Hit that notification bell. Seriously, because timing matters. When findings emerge, they'll be newsworthy for days before mainstream media moves on. Being notified immediately means you're informed while discussion is active, while you can participate in comment sections and forums, while your engagement contributes to keeping the story visible. Drop a comment right now. Tell me, based on everything you've heard, do you think 3I Atlas is a natural comet with unusual but explainable characteristics, or do you think something more significant is occurring? Don't just lurk, participate. Your perspective matters because this is a global conversation. And tell me where you're watching from, because this campaign involves observatories on every continent, researchers from dozens of countries. And the story belongs to everyone, not just those with professional access. Share this video if this information feels significant. If the questions we've raised resonate with you, if you think others should be paying attention, use whatever platform you prefer. Reddit is Arid Space, and Arid Astronomy communities would find this relevant. Twitter, if you're active there. Facebook groups focused on astronomy or space science wherever your communities gather, because the more people watching, the more pressure exists for transparency. The more questions get asked, the harder it becomes for inconvenient findings to disappear quietly into proprietary embargoes or classification restrictions. You're not passive observers. By watching this video for this long, by engaging critically with these questions, by refusing to accept surface explanations without scrutiny, you're contributing to oversight. Science functions best with public attention. Transparency emerges when people care enough to demand it. Your attention isn't incidental, it is essential. And approach the next 3 months with appropriate balance. Don't assume conspiracy where routine procedure explains observations, but don't assume routine procedure where documented anomalies suggest something genuinely unusual. Stay skeptical of sensational claims. Stay equally skeptical of dismissive explanations that ignore evidence. The truth, whatever it is, deserves investigation grounded in data rather than predetermined conclusions. 3I Atlas is out there right now, moving away from us at 210,000 kilometers per hour. It came from beyond our solar system, from a star we can't identify, from a stellar environment that might not even exist anymore. It is visiting us once, briefly, and then returning to interstellar space forever. We have one chance to understand it. 1 2-10-month window, one opportunity that ends definitively on January 2017. Everything we learn in this window. Everything we miss permanently. And the fact that humanity's planetary defense network is treating that opportunity as worth unprecedented international mobilization tells us something. Maybe it tells us we're learning to be prepared. Maybe it tells us we're cautious. Maybe it tells us they see something in the data that we don't yet have access to. But it tells us this matters. That much is certain. October 2010 1st, 2020-5. International Asteroid Warning Network activates. November 20-7th, 2020-5. Global coordinated observations begin. January 20-7th, 2020-6. The campaign concludes. Between now and then, we discover whether 3I Atlas is just another comet passing through, or whether it is the beginning of understanding that the universe contains surprises we're only now becoming equipped to recognize. Stay vigilant, stay curious, keep watching. And whatever happens over these next 90 days, remember you were paying attention when it mattered, when knowledge was being created, when answers were still uncertain, when asking questions was more important than pretending to have definitive explanations. The campaign is launching. The observations are starting. History is being written in real time, and we're watching it happen.